Okay, so first, go into our calendar. We're almost to the end of the semester. All right, we're on December 8th right now. Means we got about a week and a half left, guys. This is our lesson. This is the last time we're going to get some new content. We're finishing up section 5.3, specifically looking at independence and what independence is. Some of you chose to already do all of the chapter 5 self-assessment. And of those, if you're one of those people that have submitted it already, the error that was on most people's submissions who turned it in early right now is not knowing what independence is. So if you've already turned in the chapter 5 self-assessment and you learned something new today, you are more than welcome to resubmit that assignment. But that's up to you. I just want to put that out there. We'll have our last discussion board today about independence. And then on Thursday, we will have a review for chapter 5, which I'm working on putting together already. So hopefully that'll be a good thing. Then next week, I'll see you on Tuesday during period 5. And then I will not see you again until Friday, the last day of finals. And just as a reminder, the day of finals, that is, since your final is on the 18th, the 18th is the last day that I can accept work, right? By the end of the day on Friday, that's it. I gotta shut everything down, get all my grades put together, and have my grades submitted, all right? So please, anything you're working on, anything you're planning on working on, needs to get in by December 18th. The day of the final, if you have not submitted all of the self-assessments, which we have 4, that's essentially your ticket to be excused from class that day. Once I've confirmed that you've submitted those, you have the options being done. If you're happy with your grade and all that, if there's other things you'd like to do and like to turn in, I encourage you to stay in this live session so you can work on those things and get help if you need it as you're working on any assignments you're trying to turn in. Essentially, the whole point of the day of the final is to make sure that you get a grade you're happy with and that you at least pass the class. And that's the goal. All right. So that's the last couple weeks here. Got a couple other things I want to talk about. First, do this. All right. One thing I wanted to talk about is the discussion board from Thursday last week. There is a very weird and common error. I'm not sure where it came from. There's a whole group of people who have submitted this assignment who decided that there was a third type of computer being produced. So there had probabilities for desktops, laptops, and tablets. I'm not sure where the tablets came from. If you had that in your answer, I made a comment about it because it was very odd. Most of the people who considered tablets as the third option of computer also chose to ignore New York. And so they only had California and Texas as the first 2 branches to start. Just to clarify, there'll be a start point, which is Missouri, the distribution center. From there, there are 3 branches, California, Texas, and New York. Each of those branches has 2 branches, laptop or desktop. Okay, so your tree diagram should follow that kind of order. Again, I do not know where the tablets came from, and I do not know why New York was omitted. That was a oddly common error. So please be aware of that. If you are looking to Google to help you with this problem, please confirm that it is answering before you copy stuff down, that it's answering the question being asked. Okay, thanks. So then, I'm gonna Jump into here. There's other things I wanted to address before we get into the new content. But first, as it says right here, it is Tuesday, December 8th, 2020. We're completing section 5.3, conditional probability and independence. Today, specifically looking at independence. But first, some reminders. This is the last day of new content. Thursday's class will be a review. All assignments are posted. Today's discussion board is the last new assignment for the semester. The free response portion of the Chapter 5 self-assessment is a file upload submission. If you're taking pictures of your work and have work that you've done by hand, and there's more than one page, I suggest you add your pictures to a Word or Google document and upload the file for that document to the submission area. You can only upload one file for the file submission. All right. So either take multiple pictures, put them all in one document and submit the document, or if you're using your phone to take pictures, you can download like a scanner app, like a document scanning app, that will allow you to scan multiple pages and have those all be a single file. That's an option. All right. Bottom line is, you can only submit one file to the file upload area. So arrange your stuff accordingly so you can get it all in one shot there. Though I have had students who turned in the Chapter 5 self-assessment already that just added the extra pages to the reflection question and let me know that that's why they're attached there. All right. So all of those options will work. I'll figure it out. If they're there, I'll find them. And if they're not, I'll send you an email asking for them. All right. Any questions before we jump into the new content? Anything I can clarify? Okay. Here we go. Easy. All right, so what is independence? So we're going to consider two examples that we've seen previously in this chapter. One is tossing the fair coin. One is the pierced ears example. Right? This is the example that took the statistics scores, the college statistics scores for the 178 students, made a two-way table between gender and whether or not they had their ears pierced. Reference that example. And we're all familiar with tossing a fair coin. There's a 50-50 shot of it being heads or tails. All right. So when tossing a fair coin, probability of getting a head first, event A, and the probability of getting a tail second, event B, they're both 0.5. The chances of first tossing a head and then getting a tail on the second toss can be given as follows. Probability of B given A is equal to the probability of A and B divided by the probability of A. Okay, this is our conditional probability rule. And that's equal to 0.5 times 0.5 divided by 0.5, which equals 0.5. Right? The probability of the second toss does not change despite knowing what happened on the first toss, right? Coin doesn't know anything. It has no brain. Doesn't care. It doesn't know that it was flipped previously, and it doesn't know it's going to be flipped again. It just gives results. You already flipped a head, has no bearing on whether or not the next flip will be a tails. In our other example, our two events were A, student is male, B, student has pierced ears. We all know the following. Based on the work we've done, the probability the student is male is 90 out of 178. Probability the student has pierced ears is 103 out of 178. The probability that the student has pierced ears given that they are male is 19 out of 90. Knowing that a student is male changes the probability that the student has pierced ears. We can see this because probability that a student has pierced ears given that they're male is 19 out of 90, and that is not equivalent to the probability that a student has pierced ears in general, right? 103 out of 178. So having the information that the student is male to start changes the likelihood of selecting a student with pierced ears. Right, so knowing the first outcome has an influence on what the second outcome could be. This is kind of the basis of what independence is. Okay. So when knowledge that one event has happened does not change the likelihood that another event will happen, then the two events are independent, right? Meaning one event does not influence the next event. That makes them independent. Right? We have our book definition. Two events A and B are independent if the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if probability of A given B is equal to probability of A, and probability of B given A is equal to the probability of B. Okay. This last sentence in the definition is very important. It is a conditional sentence, a conditional statement. And if you guys remember back to Math 3, one of the chapters you guys talked about was, these conditional events, conditional statements. You have an if-then statement. Right? In this case, in order for us to be able to conclude that two events are independent, right, we need both of these things to occur. That's the significance of the and here. So if two events are independent, or if two events are independent, then this had to have happened. Probability of A given B equals probability of A. Probability of B given A equals probability of B. Both must happen. If only one works and the other one doesn't, they're not independent. Okay? So this is important. This means that when you're checking or determining independence of two events, you need to check both of these things, right? Unless the first one you check ends up being not equal, then you're done. There's no reason to check the second one. Does anyone need a moment to write any of this down? Please raise your hand. So now we're going to look at an example of determining independence. How can we check for independence? In this example, we have 452 high school students who completed a survey were randomly selected. The survey was trying to determine if there's a relationship between gender and relative finger length. The two-way table below shows the gender of each student and which finger was longer on their left hand, index finger or ring finger. And so here's our two-way table. Across the top, we have female and male. On the left-hand side, we have index finger, ring finger, or same length, an option. All right, and we have all of our totals. The question we need to answer, are the events female and has a longer ring finger independent? Right. To make our lives easier, we're going to label these events A and B. Hopefully my pen wants to work a little better. We got A and B. So we need to check our two conditions, right? We need to see, is the probability of A given B equal to the probability of A? And is the probability of B given A equal to the probability of B? Right? The little question marks above the equal sign just indicate that this is something I'm testing. I do not know that they're equal. I want to check to see if this is true. All right, so this tells the reader, tells the viewer, I'm not saying these things are equal yet. I want to check to see if they are. All right, so let's first just identify what we know. Right? Use our two-way table and fill out some probabilities. We have the probability of A, right, which is probability that the student is female in this survey. Right? We have 212 out of 452. And the probability a student has a longer ring finger. We're going to look at ring finger being longer. Right? We have 234 out of 452. Right? Any questions so far? So far, a lot of this we've seen before. Okay, so then let's find what is the probability of A given B. In other words, what's the probability that the student is female if we already know that their ring finger is longer? Right? This is going to be equal to the probability of A intersection B divided by the probability of B. Probability of A intersection B, right? We have 82 out of 452. Probability of B, we have 234 out of 452. This ends up being equivalent to 82 out of 234. Okay. Which, if we put this in our calculator, we'll get a decimal, which is 0.35, approximately. Pen's acting wonky. Better. Now, so now we just need to check what's probability of A. We have that here. Let's do it as a decimal so we can easily check what's going on. Calculator says this is equal to 0.469. All right, we found out that this is not equivalent. The first condition we checked failed, meaning I don't even have to check this one anymore. This is not true. So the events are not independent. So this is how we use that, the math, so to say, to determine independence. Right? We know this condition holds if the events are independent. Probability of A given B has to equal probability of A. It does not. So the events are not independent. And we solved our problem. Any questions? Anything I can clarify? So we need a moment to write anything down from this example. All right. We're going to keep this moving. So now, based on these results and based on the definition for independence, we get events. A and B are independent. Probability of B given A is equal to probability of B. So the general multiplication rule can be simplified by substituting probability of B in place of probability of B given A. Right? This first equivalence here is the general multiplication rule that we've used previously. Probability of A and B is equal to probability of A times probability of B given A. This can now just be written as probability of A times probability of B. Right? So when two events are independent, we know they're independent. Either we've been told or we've determined they're independent. Probability of those events both happening is just multiplying their independent probabilities. Right? And so here is our textbook definition for this. Right? If A and B are independent events, then the probability that A and B both occur is probability of A and B equals probability of A times probability of B. Right. Again, this is something I suggest you have in your notes. If you're taking notes, can you please raise your hand if you'll need a moment to write any of this down? So let's use what we've learned. Right? In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time, or a probability of 0.4. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? So this is the question we want to answer. What is the probability of throwing 9 perfect innings in a row? In other words, probability of pitching a perfect game. To do this, we're going to jump over to OneNote and show the work there because my pen works better in OneNote and I'm going to be doing more writing. I want to be able to do it quickly. So, essentially, again, here's what we're finding, right? We want the probability of 9 perfect innings in a row. All right. This is equivalent to the probability of the first inning being perfect and the second inning being perfect and the third all the way until and the 9th inning being perfect. All right. So it's having this string of the first inning is perfect, and then the second inning, and then the third inning, and then the fourth, and the fifth, and the sixth, all the way to the 9th. Because these are independent events, the first inning being perfect, the second inning being perfect, the third inning being perfect, they're each independent events. This is equivalent to the probability of the first inning being perfect times the probability of the second inning being perfect, right? So on until probability of the 9th inning being perfect, which the probability of a perfect inning on its own is 0.4. So each of these have the same 0.4 likelihood of occurring. Right? So we have the 0.4 times 0.4 times 0.4, 9 times. Right? A little dot, dot, dot just means this is continuing until we get to the end. Right? So we can use exponents to represent this repeated multiplication, 0.4 to the 9th. And that gives us a 0.00026. So in other words, any given game, there is a 0.00026 chance of that game being a perfect game for the pitcher. Pretty slim pickings. Right? Which makes sense. There's typically not very many perfect games in a year or even in the span of a couple of years. All right. Any questions about this process here? Again, this works with independent events using the new multiplication rule for independent events. Anyone need a moment to write any of this down? Any of this example down? Right. I'll add the work to the PowerPoint slide later. Here's our next example. This one's a bit more complex. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive result. So a 0.05 probability. It means anytime the test is given, right, there's a 5% chance that test comes back positive. Right? If 100 women with normal pregnancies are tested with the first trimester screen, what is the probability that at least one woman will receive a positive result? And the key thing here is we're looking at least one. Okay, I'll explain why this is significant next. We're going to jump back over here so we can do our work. In this question, right, we have a 5% chance for a positive test or a positive result. Right? The 0.05 probability. We're trying to find the probability of at least 1 out of 100 being positive. Now, here's the problem with at least 1 out of 100 being positive. Consider what this could look like as a tree diagram, right? We have one test, 2 branches. That can be positive or negative. And then the next is the next test, the next set of branches, right? After the positive test, we could then get another positive test or a negative test. After the negative test, I could get a positive test or a negative test, right? And we have 100 stages of this that creates all the different possibilities given 100 tests. There's 100 separate calculations or 100 separate ways to get one positive test out of 100. And that's just finding out the probability of getting one positive test. Then we'd have to go through and add the probability of getting 2 positive tests. Then go back through and add the probability of getting 3 positive tests. The number of calculations gets astronomical very fast and is not worth our time. It takes too much time. So we need to find a different way to address this problem. Again, this is due to the at least one issue. Now the good thing is having at least one accounts for having 1, 2, 3, 4, all the way up to 100 positive tests. Meaning the only other option not considered in the at least one is getting no positive tests. Only one way to do that, right? So that's helpful, right? So we're going to use the complement. This probability is equal to 1 minus probability of 100 consecutive negative tests. We can also consider that to be the probability of no positive tests in this series of 100 tests. The probability of 100 consecutive negative tests, I can calculate. I don't even need to do like a ton of work. So we're going to focus on this part and then do 1 minus the result of it. All right? So everyone understand why we're using the complement. Okay. This here, right? If we call at least 1 out of 100 positive tests, okay, you're welcome, Lilian. Have a good day. Event A, this would be a complement. We're looking at our notations. Okay. So now, we're going to say the probability of 100 consecutive negative tests is equal to probability that the first is negative and the second is negative and so on and so forth till we get to the end, and we have and the 100th is negative. Right, now this looks very similar to the baseball example we just did. Right, this ultimately gets to, because these are each independent events. Now we weren't necessarily told these are independent. However, if we think about it logically, giving the test to one person has no influence on what the results for the next person who gets the test will have. Right? They're completely independent of each other. Okay. So we end up with, sorry, I skipped a step here. There's 0.05 probability of the chance for a positive. The chance for a negative equals 1 minus the 0.05, which is 0.95. So this is the probability of getting a negative test on any given test, because we have a 0.05 probability of getting a positive test on any given test. So that leaves us with the 0.95 times 0.95 times 0.95, 100 times. So we get 0.95 to the 100th power, which is equal to 0.059. All right. So there is a 0.0059 probability of going 100 consecutive tests and not getting a single positive test. So now this number goes in here. And we get 1 minus 0.0059 equals 0.9941, or 99.41%. Right? This answers our question. Right? This is the probability of at least 1 out of 100 tests being positive. Right? So ultimately we can say there is over a 99% chance of at least one positive test out of 100. Okay? And so this is how we can address those situations where we have that at least one scenario where calculating all the probabilities directly, it's just going to be too much work, right? It's just not going to be worth it. It's just too much. There's too many ways to satisfy that event. So we look on the other side that has fewer cases to consider. What can I explain further for you guys? Is there anything that doesn't make sense? Do you have any questions? Does anyone need a moment to write anything down? Okay. So then, just to clarify, mutually exclusive is not the same as independent. Right? This is a very common misconception. Some of the students who turned in the Chapter 5 self-assessment early made the mistake of thinking that when I was asking about independence, that I was asking if the events are mutually exclusive. These two definitions are not the same. These two things are not the same. Two mutually exclusive events can never be independent, because if one event happens, the other event is guaranteed not to happen. Right? Knowing one event has occurred changes the likelihood the other event occurs. Right? Our definition of independence says that knowing one event has occurred does not change the likelihood the other event occurs. So this is exactly the opposite of the definition of independence. Right? Consider the two events. A, person is male, and B, person is pregnant. These events are mutually exclusive. Right? Person can't be both male and pregnant. However, if we know the person is male, the chance of them being pregnant is 0. We also get to the probability of B given A is not equal to the probability of B, so the events are not independent. Okay? So mutually exclusive means not independent. So if you're being asked, hey, are these events independent? If you know they're mutually exclusive, that's enough evidence to say that they're not independent. Right? So you can use a logical reasoning to that and not have to do the math. Right? If you know they're mutually exclusive. Or you can show that they're mutually exclusive. Any questions about this? This is a very common error that students have. All right. So this concludes Chapter 5 of probability. We had randomness, probability and simulation, probability rules, conditional probability, and independence. That is in the entirety of Chapter 5. So, lastly, we're going to look at the discussion board for today. Actually, first, In our live class resources today, there are some extra videos. Right? These are examples from the textbook that have little videos attached to them. Right? How to check for independence, how to work with independence in the multiplication rule, and another example of finding the probability of at least one, similar to the last example we did. There is also an AP Daily video, right? Explaining how to determine if two events are independent and calculating probabilities for independent events. So again, there's some extra resources here available for you guys, as well as obviously the resources I normally provide will be there shortly for your class period. The discussion board. There are 2 questions on here. The first question has 3 parts. In the first question, you are just determining whether the events are independent. You might be able to logically determine if the events are independent. You might need to use math, right? Showing that the probability of A given B is equal to the probability of A, probability of B given A is equal to the probability of B, or show that that does not work to prove dependence or not independence. Question 2 is actually doing a calculation based on events being independent, right? Similar to the examples that we've done. So please make sure you answer both questions.